Good afternoon. In this lecture, we will discuss about GNSS and its current advancement in GNSS technology. When we talk about the GNSS, it is a basically common name, Global Navigation Satellite System. And you know about the GPS and like Indian Regional Navigation Satellite System, IIRS. These all are various constellations which come, if we take the common name, it comes under the Global Navigation Satellite System. Similarly, we have constellations from the Russia, that is basically GLONASS, and the Galileo from European Space Agency. And in our India, we have an Indian Regional Navigation Satellite System, IRNSS. And when we talk about its another name, that is basically NAVIC, navigation with the Indian constellation, and this is a more common name basically. So what these constellations provides us, these all constellations give us the position, the coordinates, the latitude and the longitude information of a particular point. So these, when we get the coordinates from these constellations, these are very much useful for our GIS analysis, as well as it's having an application in supply chain management. So we will see its application. Now, at the end of this session, you all will be able to understand the basic global navigation satellite system concepts and application of GNSS in GIS, functioning of GNSS, and we will also discuss about the coordinate systems and the map projections, because it's very important when we get the coordinates from one from the receiver in a one coordinate system, and when we do the GIS analysis, and suppose sometimes we need to transform or convert this coordinate system one to another one. So, so we will also see the coordinate system concept. When we talk about the GIS analysis, it is in the application in the GIS of GNSS. We can take an example of geotagging. So in that, what we do, we generally take the coordinates of a particular point or any. We attach a coordinates to a basically geographical objects. So that is basically a geotagging. So how we are getting these coordinates? We are getting using the basically any like a receiver or from the any constellation. Maybe one receiver can track the signal from the various constellations as well. And maybe it's possible it may get the signal only from the one constellation. Like your satellite, your receiver will be maybe getting the signal only from the GPS. It may not be maybe configured with other constellation like Galileo or GLONASS. Similarly, if we have some old images, like old image information of this dairy collection centers, so we have information only on paper. What we do with this paper, when we scan it and when we bring into the QGIS software, or we can say the GIS environment, so it does not have any proper coordinate system or the coordinates in that. So what we do, we just assign these coordinates to this image. So some reference points we need. After that, we can interpolate and we can assign to each pixel of this image, whatever the digitized image it is there. So we get this coordinate from the GPS receiver. We will go to some known location, and which will be visible in the plot also, means the image also, and the near means the real time when we will go to the site, and we connect the information, means coordinates using the GPS device, and then we will enter into the GIS that digitized image. So, and we have another application, site suitability analysis. When we are doing then one coordinate system to the another coordinate system, we are generally transforming. So we will discuss all these things, and we have an application of this GNSS into the SCM as well, and for the vehicle tracking, for the route optimizations, and for digital mapping. We can track the vehicle, where it is going. We are nowadays we are also seeing that like any pizza delivery boy, it is coming, when how much it is taking time from that near to point, okay, minute by second information also we can get it. Similarly, we are sending our material to the like a dairy, the milk. We have the vehicle has taken the milk and it is going to the maybe the dairy. So we can track that how much time it is taking. Similarly, we have a route optimizations, which route we have to follow, so we can get the minimum timing and digital mapping. All these applications also we are having in the SCL. So what is basically a navigations? This is a science of charting one's own route from point A to point B with respect to known references, both in spatial as well as in temporal domain. And what is the positioning? This is a science to determine one's own location in known reference frame. So when we know the position of particular person's or object location, so under comes under positioning, and when we map from one to another place, it will be coming under the navigation. So why it is important to know where you have been? Where you have been, you are starting from where and you are going to the end. So we are planning a route basically. So where you have been, where you are going, all these information we can get when we talk about the navigation. And where it is means where is the building, where is the collection center, where is the dairy information. So how we will get the coordinates of that point basically. Okay, through the coordinates of that point, the location, we can get this information. So you all might have used the GPS basically, which is a very common, means very well known receiver also, and the global positioning system. It is an all-weather space-based navigation system developed by the US Department of Defense to satisfy the requirement for the military forces to accurately determine their position, velocity, and time in a common reference system anywhere on or near the earth on a continuous basis. So what is this basically? It's developed by US Department of Defense, the global positioning system. First they wanted to just put for the military purposes, but now also they are having a basically some information and the precise information for their military forces only. And we are also using for basically this information for the our what we can say means our daily uses or our particular purposes. In 1973, the US Department of Defense decided to establish, develop, test, acquire, and deploy a space-borne global positioning system (GPS), resulting in the Navistar GPS. We also call it as a Navistar GPS. That means navigation, satellite timing, and ranging global positioning system. So when we talk about the GPS general characteristics, it's developed by US Department of Defense and it provides accurate navigation. We can get the accuracy of around 10 to 20 meter also using this constellation. And it is the important thing is that it is having a worldwide coverage, and it's a 24-hour access. We can get the position all over, means throughout the day, 24-hour access it is there. It's a common coordinate system it will be having, and it is the design to replace existing, means if any satellite is like it is not working, we can replace immediately. And navigations systems and accessible by civil and the military. So these are basically used for the civil and the military applications. In this GPS, we have three segments. One is the basically space segment. Another one will be having a control segment. You can see here, this is a control segment. And then finally, we have a user segment. So in the space segment, what comes? There are the satellites. Okay, so whatever the satellites which are orbiting around the Earth comes under the space segment. Secondly, from the ground, what we are doing, we have two types of station. One is having a master control station, another one will be having a monitoring stations. So what the monitoring station do, they continuously monitoring or tracking these GPS satellites. And information, whether, see, satellite is also when it is orbiting around the earth, it is feeling so many what we can say forces. It is not like it is a fixed at a one place. It is orbiting, it is continuously moving and feeling means feeling so many forces on its faces, or what we can say solar panel. So the information when about the whether it is satellite is in correct health or not, it is monitored by the monitoring station. And this information finally, and these monitoring stations are all over the world, what we can say. These monitoring station collect that information and will send to the control segment, the main station, that is called the master station. All centers, all station monitoring station will send this information to the master station. Master station will process that information, and then it will tell how much correction is required in a particular satellite. Whether satellite is revolving in the correct path, then this correction is not required, and whatever it is there related to the satellite information, it will assess the things. And finally, this will be sent through the ground-based antennas to the all satellite, that information, and satellite finally will be storing that information. Okay, and also the along with that corrections, it will be having some position information, means satellite knows that where I am, where the position it is there. Okay, that position basically is determined in terms of the basically you can say the x, y, z coordinates and the x dot, y dot, z dot. One is the position, another one is three are the velocity. So you can understand in the position we measure in the three-dimensional dimensions. So it will be x, y, z and x dot, y dot, z dot. So this position will go to this information will go to the satellite. Now satellite is having this information. Suppose every 2 hours this information is updated. So satellite every 2 hours will be having a new coordinate at a particular time. The coordinates will be having a particular time. So like 2 o'clock, 2 hours, 4 hours, and we talk about in the UT, universal time. Then we have this satellite, from this satellite transmit this information. And then finally we have a user segment. What this user segment does, this collect the information from the, this receive the information, what we can say, the signal from the GPS satellite. In that signal, the satellite position information it is there. Means the satellite x, y, z or x dot, y dot, z dot, that information will be there. So, and one more thing will be there, the satellite, whatever, suppose x time it is sending a signal, okay, and your receiver what will we do, after suppose 1 second it is means or t second it is receiving the signal. So we know the difference, the time, suppose x, then receiving time will be there x plus t. Okay, so the time difference, how much it will be there? It will be a by t, x plus t minus x. So it will be a t time. So in t time, that signal is receiving from satellite to the receiver. That t multiplied by the velocity of light, if you do, then we get the actual distance, the range between the satellite and the receiver. So that is the basically how this satellite functions basically. Okay, how this complete GPS system works. So in the space segment, what is there? GPS is a worldwide radio navigation system. It is having a 24 satellite in a constellation, and you can see there are the these 24 satellites generally are in working condition. Apart from that, there are some redundant satellites as well. So if any satellite it is not working, it will be replaced by some other satellite. Now they are orbiting in a 6 orbital plane. So in each orbital plane, how many will be there? So you can understand like this: one orbit, this blue line, the slanting line you can see here. These are the basically orbits. The 6 orbital planes are there, 1, 2, 3. In each orbit, there will be a 4 satellite. Okay, the constellation is made such that at any time, at any point on the Earth, minimum 4 satellites will be visible, which are required to estimate a position. And these orbits are having a 50-degree inclination. So inclination is just like a angle between the equator and the orbital plane. So 55-degree, it is an inclination. Orbital period, it is around 12 hours. So it means it's taking 12 hours from to complete a one revolution. And altitude is around 20,200 kilometer approximately. So when GPS satellite are above from the Earth, how many altitude? How much altitude it is there? It is at 20,200 kilometer. Now, when we talk about our IIRS, these satellites are having almost 36,000 kilometers. Okay, so the difference is there between 20,000 and the 30,000 means 36,000. Why we have not gone up for 36,000? Because we just wanted to because when we have a 20,000 kilometers, suppose, so orbital period is around 12 hours. So 12 hours means it will be having a 12-hour visibility over a particular location. Suppose in India at a point it is having a 12 hours location, 12 hours visibility. But we want continuously. So there are two things. Either we should have so many satellites like 24 or 50, 24 or 30 satellites in an orbit, so continuous coverage it can give. So one satellite is suppose visible for 12 hours, so another set of satellite will come and it will be visible. So like that situation will be there. Or we should place satellite at such a place where we can continuously get the signal, from where we can get the continuously signal. So we have placed our satellites such a 36,000 means IRNSS constellation, 36,000 kilometer. So from there it is almost moving with respect to the that is called the basically geostationary or geo-orbit or geosynchronous, means geo-orbit we are calling, when we are placing a satellite on a 36,000 kilometer. When we are having a 20,000 kilometer, it is a medium Earth orbit. And when we are having an imaging satellite, like taking a picture means on the Earth, that generally we are putting, because image we have to take, so we have to put it closely. Okay, so 700-800 kilometers generally we are putting these satellites. So our IRNSS is having a 36,000 kilometer. Remember this thing. And it is a 12-hourly orbit, GPS in view of 4 to 5 hours, designed to last 7.5 years. And it was in launched in the different blocks like 1, 2, 2A, 2R, 2F. Considering satellite as a reference, we calculate the position on the Earth. So we can see here, this is the basically master control center. These are the basically control centers, and ground antennas are there, triangle points, and these are the basically monitoring stations are there. Okay, so like that, these are spread in a different location throughout the world, from where data is coming to the basically master control station, and from there they are assessing, and then they are sending it through ground-based antenna to the satellite. That information, that is the basically what we call it the satellite position, x by z or x dot y dot z dot. These x by z, x dot y dot z dot, that the Cartesian coordinate information, it also can be converted into a Keplerian element. And when we talk about the Keplerian element, we have a semi-major axis, or eccentricity, in the inclination, right ascension of ascending node, or what we can say, argument of Parisi, and the anomaly. So all these 6 parameters can be converted onto the Keplerian element as well, which we are that information why I'm telling, because this information is coming from the satellite to your receiver. Your receiver is reading that information, and that based on that only estimating its own position. Who uses it? So everyone, merchant, navy, coast guard vessels. Forget about the sextant, LoRa. These were the earlier used technology when we before this GPS for the navigation purpose. Commercial airlines, civil pilots, surveyors, commercial truckers, hikers, mountain climbers, cars. Now being cars or vehicles are what I mean to say vehicles. and communication and imaging satellite also having a now GPS, space to space navigation we are using. Any system which are required accurate timing as well, we are using all these places this GPS. And why we use the GPS? Because it is the weather independent, in all weather it is working, and it does not require line of sight information, means the object should not be in the same line, gives the high geodetic accuracy, can be operated day and night, and quicker and require less manpower. Economical advantages are there, and common coordinate system everywhere, wide range of application, and its price is also competitively less as compared to others. So as now your receiver is receiving the information, as I told you, the GPS satellites are transmitting the X, Y, Z information, means its position at a particular timing. So X, Y, Z information each satellite will send to the receiver. Now receiver will receive the signal from the different satellites which are coming into its visibility. Okay, now so minimum 4 satellites are required to estimate its position. So you can see here one satellite row 1, row 2. What is row 1 and row 2? As I explained to you, that the timing that satellite will send a signal to the receiver. Suppose it is a X, and the timing the receiver will receive the signal after time T. So X plus T. So the time difference will be there between the both the thing, X plus T minus X. The time will be T, and which will be multiplied by the velocity of light. We will get the range information. So the distance between the satellite and the receiver we will be knowing. So we have a row 1, the distance from one satellite, row 2, row 3, and row 4. So for these set of equation to determine the position, user position X, Y, Z, and clock bias C. So now X1 minus, now one more thing we know, suppose X1, Y1, or what we can say UX, UY, UZ. UX, UY, UZ are the user's location. Okay, users means your receiver you will be carrying in your hand, that's location. Suppose, so what you will do, and CB is the basically clock bias. So when we find out the distance between the two object, it's a very simple formula between the two object difference. It is there. It is a x square root of x1 minus x square plus x2 minus x1 minus x square plus x2 minus x square plus x3 minus x square root of that. So 2-point distance we can find out using this. X1 is the coordinate of, suppose, x1 satellite. Ux is the basically coordinate of the receiver. Similarly, u1 minus uy square plus z1 minus uz square plus rho 1 minus this will be equals to the distance. The distance one way we are finding using the coordinates, and the another side the distance we are finding using the timing. CB is the basically clock bias in the receiver. Okay, so now we can see here 4 unknowns are there, ux, uy, uz, and cb, and we are having a 4 equations from 4 satellite. So that way we can solve it and we can determine the position of x, y, z. Okay, that means we can find out the position of our receiver. So this is basically a mathematical aspect for the position estimation by a receiver using the 4 satellites. We can also visualize this thing, how it works. So suppose it is a satellite 1, okay, and then maybe it's when we talk about the receiver is receiving a signal, we don't know how, where somewhere in the sphere means the distance, whatever the row it was coming, and with that row, what we are doing, the distance, whatever the row 1 was there, suppose row 1 distance was there. So with that distance, I am making a sphere around the, keeping in this satellite in a center, I am creating a one sphere. Okay, so I have created one sphere with the radius of row 1. The receiver may be somewhere on the surface of this sphere. Okay, how we are estimating the position? Just visualize it. So what will happen? The receiver is actually somewhere on this sphere. Now what we are doing? The second satellite I am taking, and this is also receiving a signal from the receiver is receiving from this satellite also. Okay, so the row 2, the distance will be row 2, and with this row 2, what we will do? We will again create some another sphere which will be definitely cutting the previous receiver at a certain places. When two sphere intersect, we get a one circle information. Okay, we will get a one circle when two sphere intersect. Now we will take the third satellite, and definitely it will be also, because somewhere it will be past the similar phenomena will be applicable there also. The receiver will be lying on the surface of the third sphere as well. So this is a suppose third sphere. Now third sphere, wherever it will be there, whatever the circle was there which came after intersection of the two sphere, that circle will be cut by the third sphere at 2 points. Okay, 2 points. Now see, earlier we will be having only one sphere. We did not know where it will be there. Anywhere it can be there on the first sphere surface, that receiver. Second, when we included, we got the one circle information. So we know in this circle boundary somewhere that receiver it is there. Similarly, we can take the third receiver. With this, now we have come to the 2 points. So 2 points receiver, it will be there. Okay. So and out of these 2 points, anywhere the receiver's point will be there. So we will use the 4 satellite definitely to find out where is the exact satellite of the receiver location. It is there. This is just a visual concept to understand how it estimates. Presently, we have various navigation constellations which are working. GPS from US, GLONASS from Russia, Galileo from European Space Agency, and we have our own indigenous system, IIRS, Indian Regional Navigation Satellites. The chips, or whatever we can say, the receivers, we can get from all these constellations. And we have an augmented satellite-based navigation system as well. So these are the basically global, and these augmented things are there. What we do, suppose GPS satellite it is there. Our receiver will receive the GPS satellite signal and it will estimate the position also. But what we are doing, we are some local information we are getting, like ionospheric correction or tropospheric correction or different type of corrections information, because it is just using some coefficient or model based information. Okay, so some corrections at local level when we are doing, what we are doing, we are transmitting our local correction information to our satellite. Okay, suppose in India we are transmitting this satellite information to the GSAT 8 and GSAT 7. These are the basically geostationary satellite in our geo-based satellites. Okay, so from there what will be there, these again will be transmitted to the receiver. Now our receiver will receive the two type of signals. One's from the GPS, another one from the corrections from the because locally information correction, it will be more effective for the precise estimation of position. So this will also receive the signal from the different geo-based satellite. Okay, so it will give the more precise position information. Okay, so that is called the basically augmented. We are taking a support from the another satellite apart from the regular constellations. So similarly, we have a vast wide area augmented system from the US. Similarly, multifunctional satellite augmentation system, IGNOS, European Geostationary Navigation Overlay Services, and we in India we are using GPS IDET, means GPS signal we are using, in that extra information we are adding using the geo satellite. Okay, so GPS IDET, geo augmented navigation system, and the compass navigation system. So these are the augmented system, and these are our regular navigation system. So we use the there is another concept of the triangulation and the trilateration. Triangulation, what we are using generally in warehouses, we are using this technology also to track this means item. What we do, the point one at the point two means two places. Suppose beacons will be there, and the third point, that's the location we have to find out. We are using this technique where the triangle we will make, and we know the distance of the point one and point two, and between point two and the point one and point two, that is called the baseline, and the angle at which the point three it is there. So the point three means the object or the item will be having some RFID or Bluetooth level energy chip, and which is transmitting this signal. This will be received by these beacons or the receivers. And based on that, we can find out its position. Okay, so this is a basically triangle based information where we need to know the angle information and the distance between 2 points. But these are more not that much common, but still it is used in the basically what we can say warehouses. So so we are mostly using this trilateration. This is like something like similarly just now I have explained using the 3 satellites data. So one satellite, one sphere, second, then third. When we will intersect, we can easily find out the position where the object it is there. Okay, so these are the basically 2 techniques which generally we used in the indoor asset tracking. We have various GPS tracking devices, which are basically the prices of these devices basically working means varying with respect to their services also and the hardware quality as well. So one is like a server refresh rate when we are seeing is data whatever way like suppose it is updating after 10 seconds, it is updating after 30 seconds. So when it is refreshing data at a 10-second interval, it will be more costly than the 30-second interval. And similarly, the hardware quality, there is a wide variety of hardware available in the market and their prices differs a lot. Generally, cheap services provide you low quality hardware to ensure their margins. Warranty period, generally companies who provide cheap trackers at prices near 1700, 1800 does not give the after sales support and dedicated customer services. So when you are having a problem in your device, so immediately customer support should be there, and the people should come and they should immediately find out what is the solution. Okay, so all these things when we need to see when we are choosing a GPS devices, tracking devices for our vehicle or for our maybe any dairy or any milk van type of thing. Okay, so this was all about the basically GPS. When this GPS, we are getting some coordinates. Now I am shifting this to the our GIS based analysis. So what is happening in this when you have suppose this was the like dairy example you might have seen. These are the collection centers and dairies and Dehradun, all these things. So we have tagged these points using the GPS coordinates. Okay, now GPS coordinates are attached with this. Down, if you see the coordinates, it is written 78 point something 06 and 30.21. If you are able to see the bottom, you see from this is from the QGIS software we have taken the snapshot. Now, if you see the another image, now what you are seeing here some different number you are able to see. Why? The same image and that was there. Earlier it was 78, now some. So what is happening? The earlier one image what we are having, like it was in WGS 84 coordinate system. Okay. Now sometimes what is happening? We need to transform to the another coordinate system. Okay. Maybe the particular coordinate system may not work for that another one for particular type of specific type of application. Suppose these are here. How many layers are there? See, Dehradun bulk chiller, dairy, Dehradun, all keys in line, staging, village collection center, all these things are there. So these are the various layers in GIS layers. Now what is we are doing? Suppose now what this suppose one layer is having a different coordinate system, WGS 84. Another one will be having a WGS 84 UTM 44. Another one will be having a suppose some XYZ coordinate system. Now, all these, suppose 5 layers are now in a different coordinate system. So what we need to do, and you have to do some network analysis. Just before me, that lecture was going on the network analysis, and you need to perform the network analysis or whatever the editing or any other specific analysis you have to perform, GIS based. So what you have to do, you need to perform, means transform all coordinate system from the different layers to a unique one. Means you decide whatever you want, WGS 84, okay, WGS UTM 44, okay. So you transform these coordinate system into a unique one, and then you perform your analysis. So then only your analysis will be correct. Otherwise, if you use the different coordinate systems and different layers, then your analysis, whatever you are going to do, is may not be correct. Okay, so you should have some unique coordinate system. You can select anyone, and that also depending on your requirement. It is not like we can select such a coordinate system which can distort our images or distorts our area, that we can't select. Okay. So for surveying and mapping, most of the measurements are taken on the Earth's surface. The surface of Earth is an irregular surface. Directly using these measured values for further computation of distances, area, volume will give wrong results, because the irregular surface of Earth is not mathematical. So as you understand, our Earth surface is not like a regular surface. It's not like a smooth surface. It is a irregular surface. What we do, we need some mathematical surface which can closely represent our Earth. So our Earth is best represented by an ellipsoid. Okay, so there is a concept of the datum. So that's what I will come to that point. So Earth is not perfectly spherical. So how to represent the shape of the Earth? So if we have a circle, and if you see that's a radius, and double of that radius will be the diameter. So if you rotate the diameter, the circle about a diameter, you will get a three-dimensional image that is called a sphere. Just imagine that. And if you just press this, those who are not from mathematics background, for them I'm telling, otherwise ellipse is a mathematical geometry which you can easily understand. And otherwise you press this circle from top and the bottom. Okay, so it will be looking like a ellipse, this type of shape. So what happened here, the diameter which was in horizontal position, which is just stretched, and whatever the vertical position it was there, it is just shrunken. So the shrunken one, the shorter one, we call it as a minor axis, and the horizontal one we are calling as a major axis. And when we rotate it about its minor axis, the three-dimensional geometry what we are getting is called an ellipsoid. Okay, you remember you have to rotate it minor axis. Here only diameter was there, circle case, but in ellipse case it is a diameter, it is a minor axis. You have to rotate it. So you just imagine the three-dimensional geometry, whatever you are getting, it is called an ellipsoid. Okay, and our Earth is best represented by an ellipsoid. And that ellipsoid is a mathematical surface which can be operated by rotating an ellipse about its minor axis. Such ellipsoid is called an oblate ellipsoid. And the semi-major axis, we are representing the basically ellipsoid by these things: semi-major axis, semi-minor axis, eccentricity E, and flattening coefficient F A minus B. Okay, a reference ellipsoid has its center, a close approximation of center of mass of Earth, and minor axis is parallel to the axis of rotation of the Earth. So latitude, longitude, and the ellipsoidal height are defined on this reference ellipsoid. So latitude, longitudes are defined on this reference ellipsoid. So any point how we are finding the position? Suppose this is a point P. We are just drawing a perpendicular which will be to the surface, and the distance from surface to the P is called the basically ellipsoidal height. And wherever it is cutting the surface, it will be meeting to the means axis of rotation or the center line, and the angle from this equator to this blue line, whatever it is coming from the P point, is called the basically phi, that is the latitude, and that from the Greenwich meridian, if we measure the angle to this blue line, if you see, this is the basically observer's meridian, blue one, wherever this blue line is cutting, and so from this passing meridian is called the observer's meridian, and from this Greenwich meridian to the observer's meridian is called the basically longitude lambda. So this is how the latitude, longitude, and the ellipsoidal height we are getting. And this is all about the three-dimensional things. You got the ellipsoid, which is the three-dimensional things, but in routine you don't need these three-dimensional things. You require only the maps. What is generally you are using. So what we are doing, the three-dimensional things we are projecting onto the two-dimensional map, and the transformation of three-dimensional to the two-dimensional map is called the map projections. This generally we are doing using the suppose like a cylindrical cylinder. So inside cylinder we will place globe, and then we will project onto the wall of the cylinder, and then we will unwrap it. So it is called the cylindrical map projection. So these are the of two, like a few famous the known projection systems are there, Mercator and the transverse Mercator. So just an example I am taking. So Mercator projection system, cylindrical, conformal, meridian are equally spaced straight lines. So if you see in that Mercator projection, what is happening, down figure you see. So we have placed a globe inside the cylinder. We have just projected onto the wall of the cylinder, and after that unwrapped it. So and after unwrapping, this is situation, it is coming, the figure it is coming. So if you see the Greenland, the picture, and you see the India, so can you see, can you imagine that in Greenland is that much big? Whether the real it is coming? So no, it is the Greenland size is not that much big. See, the Indian size is looking very small, but Greenland is looking very like continent edition. What is happening? It is happening because of the distortion at the polar end. Okay, so this projection is not useful when we use for the polar region analysis. You understood this thing? Why I was telling that time that this should be in the common format, because of this only. So may not be suitable, one projection system may not be suitable for a particular type of analysis. So you have to select a correct projection system. After getting the coordinates from GPS receiver, also there are the certain things which we need to take care while doing the GIS based analysis. So we have to select the correct coordinate system. Okay, so I will select, this is for the basically Indian region, because it is telling scale is true along the equator. So scale is true means there is no distortion along the line equator. So if for the equatorial region or nearby region I can use it, but for great distortion in the polar region I will not use this kind of things for the GIS analysis. Okay, so this is just an example. This is very common. Generally, we are using Universal Transverse Mercator (UTM) projection system. It is a basically particular case of transverse Mercator. So what we have done, we have divided whole world into the small grids, so the distortion can be kept minimum within one region. Okay, so you can see here, these are the basically 6 degree grids are there longitude wise, and you see 8 degree latitude wise. So this is the grid. When we talk about the Dehradun, it is coming in the UTM 44. So if any Dehradun based analysis we are doing, so we can do it in the UTM 44 means, or you can select your area. So similarly like that. So the projection system, as I was telling you in that figure here, that you are able to see some meter things. So these are the basically UTM 44 coordinate system. Okay, WGS 84 and UTM 44. So means you had a WGS 84 that data, and after that you have projected onto the UTM projection system, UTM 44. So there are that whatever analysis you are seeing, it is in there are UTM 44 projection. Okay, so once you get the receiver, means coordinates from the receiver, after that also you have to transform it into a particular type of projection system or coordinate system to make it similar for, or to make it unique for all the layers. Then only your GIS based analysis will be correct. Okay, So thank you very much for joining this session. And if you have though I will take some of the questions, but still you have any query related to the GPS or navigation systems or projection system, coordinate system, I suggest you to write me on my mail ID. I will definitely reply. Thank you very much.